Alright, so we have electronegativity and polarity, so we're going to talk about polar molecules and how electronegativity will lead into polarity existing. So a chemical bond's character is related to each atom's attraction to electrons in the bond. So we're going to talk about how electronegativity is used to determine the bond type and what type of characteristics are covalently bonded compounds. And then what is electronegativity? If you remember electronegativity from a very long time ago, it is how much an atom wants to hold on to its electrons. This is the one I described as the good mother, bad mother. So we have the good mother is holding on to its electrons, and we can describe that being as fluorine, because fluorine does not let go of its electrons, just like a good mother would not let go of its children. So we look at the periodic table, and we have fluorine being here. Fluorine's the most electronegative, if you recall. This is where all the electrons are. This is the very tightly held electrons for the atom, and fluorine is so electronegative that it actually takes electrons away from other things. Whereas we have the contrast of francium, and francium does not take electrons away from anything, it actually gives them away very easily. So here we are talking about electronegativity and ionization energy. We can go back some chapters to review that. All right. So we're talking about how much an atom wants to attract electrons and keep them. So we can have different types of bonds. We can have bonds that are mostly ionic, so you're actually kind of taking the electron away. We have polar covalent, where one is holding on to them a little bit more. We have mostly covalent, so mostly sharing, and then we have nonpolar, where we actually have equal sharing. I like to think of nonpolar covalent as twins. So bond types come from different electronegativities between two atoms. Nonpolar covalent, it's a pure covalent. It is when two atoms are sharing electrons evenly, the same elements. So if I have oxygen, I have two oxygens attached to each other. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. These are going to be shared in a double bond. Now this guy has 8, and this guy has 8. But because they have the same electronegativity, they're going to be sharing the electrons equally. Polar covalent, we have unequal sharing of electrons, like a north pole and a south pole. And then we'll do some examples with that later. We have mostly ionic, where there's such a large difference in electronegativities that the electron is transferred for all intents and purposes. So let's look at this. We have HCl. So we have hydrogen and chlorine attached, and the electron that hydrogen brought is going to spend most of its time with chlorine, right? So then we've almost been here the whole time. So now this has a negative charge, but it's almost a negative charge. So we have this lowercase delta signifying we have almost negative charge, and here we have an almost positive charge. And here we have water, my favorite example for everything. So oxygen is more electronegative and keeps the electrons. So then the electron that came here, it's gonna, with the hydrogens, are going to stay with the oxygen most of the time. So it gives oxygen a sort of negative charge, and it gives hydrogens a sort of positive charge. So let's talk about how they interact together. Oh, by the way, this would be polar molecule. Water is polar. Let's talk about molecular polarity. Non-polar molecules are not attracted by electric fields, whereas polar molecules are attracted by electric field. This is because the electrons are not evenly distributed, and it creates a slight charge. So what does polarity have to do with the shape? We just talked about shape. So how come some are polar and some are not? Let's consider water again, and let's compare that to CCl4. They both have electronegativity differences, right? We have carbon and chlorine. Chlorine's way more electronegative than carbon, and oxygen's way more electronegative than hydrogen. So both of them could be polar, but only one of them is. So then we have oxygen and hydrogen, and the oxygen is taking the electrons away from the hydrogen, and it's keeping them, making it slightly negative. But with carbon, we have 1, 2, 3, 4 chlorines, and the chlorines are taking the carbon's electrons, but because they're evenly distributed, there's no polar side. This side isn't more negative than this side because they're equal. So that's why CCl4 is nonpolar, but water is, because water does have a side that is slightly more negative. What about ammonia? Ammonia has nitrogen with 5 valence electrons. We have 1, 2, 3, 4, 5. We have hydrogen here, here, and here. Because nitrogen is more electronegative than hydrogen, we can get the electrons out of hydrogen into the nitrogen. So the nitrogen is slightly more negative. Do you think nitrogen here would be more negative enough to make ammonia polar? Alright, and here's just me doing bad three-dimensional shapes that I'm not good at this, but the shape of water is bent, if you recall that from the last video. The lone pairs push the hydrogen down. The asymmetric bonds cause a definite positive and a negative end, causing the water to be polar, whereas the CCl4, we have a tetrahedral. There is symmetry in the negative bonds. They're equal on all sides, so there's not one more positive than one more negative. Remember, polar and nonpolar molecules don't mix. So let's think of oil and water. If we know that water is polar, what do you think oil is? Intermolecular forces can also be called van der Waal forces. Van der Waal. The forces between molecules, and they're weaker than bonds in the atoms. Van der Waal forces. We're going to talk about 3 intermolecular forces. So we have the dispersion force. The dispersion force is between nonpolar molecules. Dipole-dipole is an intermolecular force between oppositely charged ends of polar molecules. Have you ever seen water on a leaf? In the morning we have dew, and then on the leaf, that's a badly drawn leaf, we may have a little bit of water. You see, you stare, you look at this drop and it never falls, and you're wondering why. Why does it not fall? Well, inside we actually have a lot of water, and if you recall, we have this with a slightly negative side and this with a slightly positive side. So then we can attach this to another, and this is positive, slightly positive, this is slightly positive, this is slightly negative. Oh, that's awful. So we're attaching these, and because they're attaching, they actually spin in a circle and they never ever break apart. Well, these are bonds that are occurring between a hydrogen and an oxygen, and we call that a special name. We call that a hydrogen bond. Hydrogen bonds are stronger, not very strong, but there's so many of them, there's 2, and they occur between hydrogen and one dipole of either an F, an O, or an N atom. So for example, H2O has hydrogen bonds, and hydrogen bonds keep a lot of you alive. You remember this from biology class. So dipole-dipole is just between any polar molecule, and hydrogen bonds have to be with hydrogen, and NO or FN or O. Fluorine, oxygen, or nitrogen. There we go. Covalent network solids. They're connected by covalent bonds. This is diamonds. So we have diamonds, which is carbon with. We have just a whole bunch of carbons attached to themselves. and this creates a very strong network, and this network is seen in the hardness of diamonds or quartz. They're non-conductors, they're brittle, and they're extremely hard, and these are just covalent network solids. So we have carbons covalently bonded to each other. Last thing, hydride. Sometimes H2O is in between two compounds and hangs out in the structure. So here we have Epsom salt, which is a hydride. It's a heptahydride, which means 7. There's 7 waters in every magnesium sulfate crystal, and you can actually get Epsom salt, put it in fire in a little test tube. This is the lab that we're missing, because I'm not with you guys. So you put a little bit of Epsom salt in here, and it looks just like salt. This is what maybe your moms put on their foot baths. So you're holding it with the tongs, and then you're putting it under the flame, right? And you're moving it back and forth. And from the Epsom salt, the magnesium sulfate, you will actually start getting steam, and you'll get bubbles because the water, the 7 waters, are coming out. This is called these are hydrides, and depending on how many we have, that's the name we give them. This is part of your semester review. All right, hope that helped.